Great. So thank you very much. It's really a great honor and pleasure to be here today. It's such an exciting opportunity to present our work at the Federal Statistical Office. So if you were there last year, you might remember one of our initiatives around secondary usage of data, how to facilitate this secondary usage by researcher. And here today, I would like to present what we released earlier this year, which is a platform itself as an open source project called LOMAS, which aims to enable confidential analysis of data. So let me just drive you around its functionalities. So how does it work? It's fairly straightforward. So from the researcher point of view or any authorized user, the platform works as a remote access. And when you get onto the platform, you reach a Jupyter Lab environment, and then you can start interacting with your data set. So for instance, we have developed a client Python library, which enables you first to get access to metadata for the data sets that is made accessible to the researcher. And once you have the metadata that you have started to understand what is available inside the database, you can request what we call a dummy dataset, which is a completely random dataset, but which reproduces the metadata of the original dataset. And then, thanks to Mariana, there's no need to explain to you what's a data analysis pipeline, and not a differentially private data analysis pipeline. But then the next step is to use this dummy data to develop your data analysis pipeline, including a differentially private mechanism. Once the user is happy with this pipeline, he can just send it to the secure server, which will then test first if the pipeline includes a differential privacy mechanism, and second, if the user has the necessary budget to apply the pipeline on the private dataset and retrieve the results. If those two conditions are met, then the server will execute automatically the pipeline, compute the result, protected thanks to differential privacy, and then send back the result to the users and to the platform, such that the researcher can get the results, make analysis without ever seeing the data, and for the town owner while controlling automatically the risk of disclosure at any time. So the platform has been sought to be working on a trusted computing environment. So this is why it's been dedicated mostly for public administration, which can deploy such infrastructure on their own infrastructure, being, for instance, National Statistical Office or any federal agency, for instance, for us in Switzerland. So LOMAS is open source, as I mentioned, so you can go on the GitHub repo by scanning the QR codes here on the lower right corner. It's portable in the sense that every features are either a library that you can install using PyPy, or it's a Docker container that you can deploy automatically on a Kubernetes cluster. It's modular in the sense that we are not reinventing and re-implementing all mechanisms, but it relies on existing open source standards, such as the OpenDP library. And it aims to make the usage of differential privacy as easy as possible to use, mainly because, for instance, sometimes using DP can be quite intricate by just some parameters to be specified to the function. And thanks to the metadata catalog that is present on the platform, some of these parameters can be fed automatically. So if you want to know more about this platform, you can just go and scan the second QR code, and you can read through our blog, which also give you some pointers to more detail and more specifically the associated white paper. And also, if you want to experiment to see how this works, we've partnered with the French National Statistical Office, the INSEE, and LOMAS is a service that can be deployed automatically on their data lab platform, Onyxia. So if you're from academia or from a National Statistical Office, you can request access, and you can just deploy the service with a click and start experimenting either as a data owner or a researcher. So if you want to know more, do not hesitate to scan the QR codes and That was all for me. Thank you very much.
Thank you.
Next is, I believe, Sina Sham. We're getting your slide up.
Hi everyone, my name is Sina. I'm a research scientist at Meta. What I'm going to talk today is nothing to do with my affiliation. It's just a cool project that we did in collaboration with Professor Gabriel Ghanita and Professor Bhaskar Krishnamakari. It's an algorithm for the publication of household electricity datasets in a differentially private way. A little bit of background about it. Such data are usually recorded on an hourly basis, the consumption data, and governments and companies use it for variety of reasons. It's quite for planning, for, let's say, marketing. But if you actually search for such a data set online, you'll notice that there are not many of them available, almost none, and there are good reasons for it, mostly due to the privacy reasons. They are quite sensitive. You can actually find out the number of occupants in the houses, the appliances that they use, different information about them. So here is the algorithm. We start by generating this matrix called household electricity consumption matrix. It's a three-dimensional matrix. We overlay grid on top of the map, and on the third dimension, we have the time axis. Each cell in this matrix represents the amount of consumption in that particular area at that particular time. In the second step, we normalize that consumption matrix. So doing that, we are bounding the sensitivity. And then we take a small portion of that data for private training of a RNN model. It's model agnostic. I'm just using RNN as an example. In our third step, we divide the time space. The way we do create that training data and sanitize it is a pre-processing approach, is by creating this three-dimensional quad tree on top of the matrix. The way it works, let's say we have the depth of the tree is 2, we divide the time horizon into 3 partitions. For the first partition, we assume that there is a single neighborhood. As in the second one, we'll be having 4, and the last one, 16. And we aggregate over each one of the neighborhoods. So from the first aggregation, we get a single time series that would be the sensitivity. If you are doing averaging, the sensitivity would be 1/16, as we bounded the sensitivity by 1. And in the second one, you have 4 time series, and in the last one, 16. We sanitize them using Laplacian mechanism, and then we feed them all into the RNN model and have the model trained in a private way. Ultimately, we get an estimation for the whole matrix, this 3-T matrix. Recall that these are normalized values, so it just gives us a small scale of data. In the last step, we conduct this clustering, and the way we do that is by quantization of the values between 0 and 1, and that quantization gives us this partitioning of space. So these are private partitioning. Now we use this private partitioning on top of the actual data. For each partition, for each cluster, we sum up the values, sanitize them, and then make the uniformity assumption and publish the data. This algorithm has been shown to improve the performance by 20 to 50% on the data sets that we applied. So it can be quite handy. I'm happy to discuss it more with you guys, or I'm open to collaborations. Thank you.
Thank you. Oh, fantastic. All right. You're up.
Hi everyone, I'm Wenrong. I'm currently working as a research scientist at TikTok. So today I'll just showcase a simple example of how we can achieve local privacy guarantees by combining several different private privacy preserving techniques and also achieve the accuracy comparable to the central DP. So our setting is we have a bunch of devices and there's a server that wants to learn the data domains. For example, this can have a lot of applications. Like we want to learn the URLs of what our user watched. So our protocol mainly relies on the stability-based histogram. So this stability-based histogram actually was proposed in the central DP setting, but to protect against the direct data collection and also tracing by the server, we integrate the ESA framework. So basically everything is standard, except for we introduce another auxiliary server. So this auxiliary server will only receive the encrypted message and also hashed value. So this message is encrypted by the server's public key. So it will never recover the original message. Also, the hash is irreversible, so it's guaranteed. And the key of this is the hash value. The count of the hash value remains the same. So that's why we can do this histogram. Yeah. And also the message passed through the shuffler is also double encrypted. So it's very safe. So why I'm saying this is efficient, because if we were to use a pure LDP protocol, we usually have to divide the raw data into several pieces. And then the server has to reconstruct the message, and it will introduce both computation and communication cost. So I'm saying our protocol is efficient, but I have to say this is causing local privacy. It's not pure LDP. But I want to add, we do also have a pure LDP protocol for frequency estimation for other applications, for more sensitive applications. So, but because of the time, I won't cover them today. And the archive and GitHub are upcoming. Next, I'll pass to my colleague Bo to talk about another challenge and how we address that.
Good morning, everyone. My name is Bo. I'm currently a research scientist at TikTok. So today I'm going to present a recent work related to differential privacy. So TikTok has been embedded differential privacy into a lot of its data collection and analysis pipelines. But during the collaboration with the engineering teams, we realized that the engineers, they prefer a utility definition with explainable guarantees. So after finalizing their request, we formalized the utility definition on the right-hand side. So basically, they would like the output of a DP mechanism to fall within a preferred utility range with certain confidence. So that utility constraint, the preferred utility region, usually is dependent on the specific applications. Sometimes it can be data independent. For example, the relative error, and sometimes it's data independent, such as a fixed domain, a fixed output, or just the absolute error. So here, given a specific preferred region, we're considering the following two questions. So basically, is handling a better utility and the privacy trade-off. Can we, given a fixed privacy budget, can we boost the confidence rate? And given the desired confidence rate, can we boost or minimize the privacy leakage? So we came up with this privacy boosting differentially private mechanism. So basically it's a kernel DP mechanism. There's nothing different between a traditional DP mechanism, and mixing like a step function, which is defined by the boundary of the preferred utility region. So basically, it's boosting the likelihood of generating the noisy data within the preferred utility range, while decreasing the likelihood without outside this range. And we do some privacy analysis using privacy loss distribution and find out that the PLD is nothing but a linear combination of the PLD of the DP and the step function. So if you want to learn more about this, feel free to catch me in the break. Thank you.
You're just getting your slide up and then.
No, it's the next slide. I have it. Yes, yes, yes. Yes, thank you. So I can stand here in silence, but okay. So it's instead of a pitch, it's a rant, and I'm very much opposed to the use of the noun privatization when we say that we apply differential privacy to anything. And can you click? One slide. And I have dictionaries to support my point of view. So making something private is changing it from public to private control. Or if you consult OED, they are particularly evocative in their use of examples. The workers are opposing the privatization of the National Rail Company, like I kind of see a shade of Margaret Thatcher there. And is this connotations that we want to evoke, like that we want to use in when we say that we apply differential privacy? My answer is no. Yeah.
I'm skeptical of the definition on the right because
No, we do not have.
No
time for
questions
questions.
and
To break after this, so I feel free to get debating then.
yes. What about alternatives? If I kind of don't like privatization, and by the way, like again, privatization is like what oligarchs do to a country, not what we want to do to data, right? So Cynthia, the work, she likes standardization a lot. She uses this as a synonym. Recently, I've seen some derivatives of DP, like DPifying something. It's like kind of a bit of a jargon. Like I don't want to kind of. We probably should not be using it, talking to the outside crowd. But again, not every noun can be verbed. Not every verb can be nouned, right? So just use the powers of the English language. Making something private applies differential privacy to it, anything but privatization.